Assume you have a set of tokens, red and blue, laid out in a circle. Place in between each token a new token. A red one if the colors are the same, and a blue one if they are different. When we have done that, we remove our original tokens. We get a new circle similar to our original circle. This process can be repeated multiple times. Sometimes, we will end up with all tokens being the same color. If we wait just long enough. One more step. There we are. All the tokens are the same color. This does not always happen. For example, this configuration goes into a loop. No matter how many times we repeat the process, the system always stays the same. Can we find for which starting configurations we eventually end up with all the same color? If you want to try for yourself, pause the video right now. If not, keep watching to see the solution. First, let's replace our tokens with numbers. We will use 0 for red tokens and 1 for blue tokens. Our wheel of tokens is now a mathematical object that we can define operations on. First, one can duplicate the wheel. Second, a wheel can be rotated. And lastly, wheels can be combined to a new object. Here we replace 2 of the same tokens with a red token, and 2 different tokens with a blue token. This operation is called exclusive OR. The result we get is exactly the same as before. Note that these operations commute. Rotating both systems before joining them is the same as rotating the result after. And combining 3 or more systems with exclusive OR always returns 0 when our original number of ones was even, and returns 1 as it was odd, independent of the order of operations. This means that applying our procedure on 2 or more systems before combining them is equivalent to applying it after. Look at a system with only a single blue token. Each system that we consider can be built by combining systems with 1 token. This means that if a system with a single blue token ends up with only red tokens, all systems do. So we will only have to consider systems with a single blue token. Another simplification we can do is to unroll our wheel, and put our numbers on a tape. This tape is finite, but we can make it infinite by initially repeating at both ends. To turn this tape back into a wheel, we will just have to take a part of the wheel with 6 elements. It can easily be seen that shifting the tape will shift the wheel, and that combining tapes will combine the equivalent wheel. Let's have a look again at the tape. If we have the current state of the tape, can we calculate the previous ones? If we choose one number to be solid, the other numbers can be calculated. Grow the numbers from tape center and swap if the number is a 1, stay if the number is a 0. This means that if a series is periodic, the previous series is periodic with the same number if the number of ones in the period is even, and double the period if the number of ones is odd. This means that our operation can either divide the period by 2, or keep the period. As the tape with only zeros has a period of 1, this means that the tape can only become 0 if the period is a power of 2. Note that this does not prove that powers of 2 always become 0, but it proves that a period of other numbers never become all zeros. If we look back at the wheel, we can still unwrap our wheel and write our wheel as a list of numbers. If we consider a Galois field where omega is a root of 0 with order the size of the wheel, we can write our wheel as a polynomial, where we put an even number if the token is red and an odd number if the token is blue. One can easily see that exclusive OR matches summing the polynomial, and that shifting is multiplying with a power of omega. This means that applying our procedure is multiplying with omega plus 1. Powers of this expression give the binomial coefficients of Newton. If the power is a power of 2, all coefficients are even, except for the first and last one. But as the first and last one both resolve to the constant term, both odd numbers cancel out, and all coefficients are even, and thus correspond to red tokens. As an even number times an odd number is still even, the other factors in the polynomial do not matter. This means that the system reduces to 0 if and only if the period of the system is a power of 2. To look back at the wheel, the period is the smallest number of token you have to turn the wheel to return at the original setting. If the wheel does not have any rotational symmetry, this is the full size of the wheel.